Okay, today I'd like to introduce you to the force of friction. We're going to start by watching my cat come running across the living room floor and try to stop on this flyers mat. You're going to see that when he stops on the flyers mat starts sliding across the living room floor. You'll see eventually the cat and the rug do come to rest, and they come to rest because of friction. Friction is often the force that helps to bring us to rest. It helps to stop us. Remember that if there is no friction, and on this skateboard there's going to be very little friction, that once the cat starts moving, he's going to stay in motion in a straight line at a constant speed and a constant direction until eventually some force stops him. If friction's not present, however, we're going to travel until some other force eventually stops us. We can see this really well when Billy hits this hockey puck across the lake. Since the lake has such a small amount of friction, you can see that the puck just keeps going and going and going and going till eventually it reaches the other bank. We can see with Miss Gaetano on the wheeled cart that she also is going to continue her motion in a straight line until she crashes into the bleachers. Okay? Again, when friction's not present, this is important. When there is no friction, we keep moving at a constant speed and constant direction until some other force stops us. However, today we'd like to look at friction. So we're going to take a block, we're going to pull it across a table, and we want to make sure we understand the forces that are present. So you're going to have the force of gravity, the earth pulling down. We've already spent a lot of time learning about gravity. We're going to have force normal. That is the contact force between the table and the block. As the block pushes down on the table pushes back up. Now it's important to realize that the force gravity and the force normal are equal, and therefore they're going to cancel out when we're looking at our net force, and we can totally ignore them. We're going to have force applied or force tension from the string pulling the block to the right, and then where the table meets the block we're going to have our frictional force, and that's the one we want to focus on. Okay, so as we mentioned, gravity and normal often cancel, and we could ignore them when we're looking at the motion of the object. So then you just have to look at how much tension and how much friction, and what's going to happen to my actual object. So if I have a 1 kilogram object at rest, and it's subjected to these forces, I hope you see that it will start moving to the right, and it will start to pick up speed. Okay? The force to the right is bigger than the force to the left, so it's going to start moving to the right. If the two forces were equal and the object is at rest, well, objects at rest stay at rest when the net force is 0. So even though there are forces pulling on this block, it's not going to go anywhere. If the object is already moving to the right, and we have a force of 10 and a force of 8, that's going to give us a net force to the right of 2. It's already moving, so what's going to happen to it is it's going to pick up speed. A net force will cause an acceleration, and in this case it's going to accelerate to the right, meaning it's going to get higher and higher speeds. If, on the other hand, friction is bigger than tension, friction is going to dominate, and this object that is moving to the right will lose speed. It'll slow down and stop. So even though we're pulling on it, we're not pulling on it hard enough to overcome friction. So this object would gradually slow down and stop. Finally, if we have equal forces and it's already moving, then it's going to stay moving. When the net force is 0, an object in motion stays in motion in a straight line at a constant speed. So this guy would continue to move to the right at 3 meters per second. Now we want to start focusing in on what actually causes friction. Up to this point, I just told you how much friction was. Well, the first scientist to actually start to hone in on what some of these factors are that determine friction was Leonardo da Vinci. He's from the 1500s. He recorded his observations on friction in 1493, and he kept most of this work hidden from the world with most of his other scientific work. He was afraid of the backlash he would get by examining the world in a scientific manner. It's hard to imagine people not appreciating all that science could do for us. Okay, but anyway, he's our first one to systematically study friction and come to some good conclusions. And here's some things you should know about friction. This is an important graph, so let me explain to you what it's showing you. The person is using a force probe to pull on the block. We're measuring how much force is being applied to the string, and we're plotting it out on this graph. The first line I want to make sure is clear is right here. For all of this section, the block is at rest. For all of this section, it's moving at a constant speed. So when you sketch this out in your notebook, make sure you delineate rest versus moving at a constant speed. So what is this graph showing us? Well, for the first part, our force is 0, which means this person hasn't started pulling yet. Okay? The string is loose. They have not yet started to pull on the string. At this moment, they start to pull, and they pull with more and more force. The block is not moving. They're pulling harder. The block is still not moving. Okay, we're all the way up to here. They keep pulling, they pull, and this point right here is an important point. This is where they overcome friction. This is where the block first starts to move. This value, somewhere maybe around 5.5 newtons, is the force required to break the frictional grip and get this thing to start moving. Here's what's weird. Once the block starts moving, we don't have to continue pulling with that same force to keep it moving. So if we trace across, this is more like 3.1 newtons. And what this tells us is that friction is stronger when the object is at rest. Once it starts sliding across the surface, friction becomes a smaller value. Now it doesn't change once it starts moving, so I got to be real careful here. Doesn't matter what speed it's moving, it's going to be the same frictional force. The only difference is when it's at rest, the friction is higher than when it's in motion. Once it's in motion, the speed does not affect how much friction there is. Okay? Sometimes you'll hear this referred to as static friction. That is the friction when it's at rest. And they might refer to it as kinetic friction. That's the friction once the thing is already moving. You might have experienced this before in your life. You're trying to move a piece of furniture, and as you push on it, it's really hard to get it moving. However, once it starts moving, it's not that hard to keep it moving. Okay, so friction has a greater value when the object is at rest. It has a lesser value once it starts to move. How do we think about friction? Well, I want to make sure you know that even though we started studying friction back in the 1500s, we still don't have a complete picture of exactly what's going on. And each time we want to determine friction, we really have to do it experimentally. We cannot always predict exactly what the friction will be by just looking at the two surfaces. However, a good model of friction is to think about these two surfaces. Even if they look smooth to the eye, when you look at it with a microscope or even a magnifying glass, you'll see that the surfaces have imperfections in them. They have divots, they have bumps, they have valleys. And you can think about friction as the one surface getting caught on the other surface. Okay? So that's a model of friction that helps you visualize. And remember, the model is not quite perfect because sometimes you can have two super smooth surfaces, like glass on glass, and yet have a lot of friction. And we think that's because the charges in one surface are being attracted to charges in the other. The nice part is you don't have to worry about this at this point. You just have to understand how to calculate friction and use it. You don't have to know on a microscopic level exactly what's happening with your different surfaces. I do want you to know, however, that it is very complicated. Okay, so imagine we are pushing an object across our floor, and the thing that's going to stop us from moving it is the force of friction. Without friction, even at the smallest push would get this thing moving and accelerating across the floor. Okay, so we want to think about what are the factors that affect how much friction we're going to experience. Hopefully, you realize one of the factors is the type of surfaces that are in contact with each other. It's not just the type of floor, it's not just the type of wood that the furniture is made of, but it's how they combine together. So factor one is the nature of the two surfaces that are sliding past each other. The second factor that affects it is how much these surfaces are being pushed together. The harder they're pushed together, the more friction we're going to experience. So there are two factors. The nature of the surfaces, notice it's plural, the surfaces, both of them, and how hard the surfaces are being pushed together. Okay, so this is how the graph turns out. So again, we've drawn this out at the beginning of class, and now what we want to do is we want to change the force normal. We want to change how much force is pushing the two surfaces together, and what you'll see is you get a proportional graph. The greater the force normal, that is, the harder the surfaces are pushed into each other, the more frictional force you will experience. So here's the process to figure out force friction. You start by getting force gravity, mass times 9.8. Again, on a different planet, don't use 9.8, but most of the problems will take place here on Earth. The force gravity is perfectly balanced by force normal, so whatever number you get for gravity, it will be the same as your force normal. Unless something silly's going on, like maybe you're pushing down on the block. But if it's freestanding, you just set gravity equal to normal. Okay, so that's step 2. Step 3 is you realize that this is a proportional graph, y equals m times x. And then on the y, you have force friction. On the x, you have force normal. And that means the slope determines how much friction there is. It's called the coefficient of friction. The symbol that we use for the coefficient of friction is a Greek letter. It's called mu. And it usually is some number between 0 and 1. It could be higher than that, but most times it's between 0 and 1. All right? And you'll notice this is that person sliding something across their floor, that furniture. They could use magic sliders, or maybe they put some sort of leather tarp down, leather belts down that they can then push the furniture across the floor. And these are the two graphs that we get. Notice the thing that's different is the slope. The higher slope means there's going to be more friction. So the higher this number is, that mu value, that coefficient of friction, higher numbers mean greater slope. Means greater slope and greater friction. All right? So if you want to make it easy, you want to find something that has a really low coefficient of friction. If, on the other hand, you're trying to stop, like your car, you want to have a higher coefficient of friction. Okay? So a lower mu value, a lower coefficient of friction, is a slipperier surface. You will have a reference sheet, so you should try and find this in your reference packet, with a bunch of pairs of surfaces, and then it will tell you the range of possible coefficients of friction. So if you have a car on asphalt, and the asphalt is dry, it'll range somewhere between 0.5 and 0.8. There is not just one number. All tires are a little different, all road surfaces are a little different, but they should lie somewhere between 0.5 and 0.8. If I don't tell you which of these to use, take an average. If I tell you that the surfaces are in great shape, use the highest value. If I say maybe it's the worst case scenario for those surfaces, use the lowest value. Okay? So based on the way the problem is worded, determines which value you're going to use for the coefficient. Okay, I want you to realize that the things don't have to be horizontal. So if you had a book and you were holding it up against the wall and using friction to keep it from sliding down the wall, I hope you realize that friction would go against the way it's trying to slide. Gravity would be pulling it down. Friction would be holding it up. We have force normal pushing on the book from this side. That's a terrible choice of colors. Let's try this again. So we have force normal pushing from this side and force applied from the person's hand. Okay? So bottom line is friction does not have to be horizontal. Friction is always parallel to the surfaces. So if the surface is vertical, friction is vertical. If the surface is horizontal, friction is horizontal. If the surface is on an angle, like a hill, and you're on a sled, friction is going to be this green arrow. Again, it's parallel to the surface against the way the object is going to try to move. Gravity still points toward the center of the earth, and you'll notice force normal points perpendicular to your surface. Normal and friction always make a right angle to each other. Okay, I have 5 more pictures. I just want to make sure you can get the direction of friction. So in this case, I have a block of wood sliding to the right. So hopefully you would understand that friction would be to the left. Here's a block of wood that's just sitting on a flat surface. In this case, there would not need to be any friction. The block's not going to try to move, so there's no friction necessary. If you have a block sliding down an incline, friction would point up the incline. If you had a block going up the incline, friction would be trying to stop it. Friction would go against the motion of the object. And hopefully you realize if you had a block of wood that was just sitting on an incline, it wants to move. So friction opposes that motion that would happen if friction was not present. All right? So make sure you can identify the direction of friction. Finally, I have a few more. We've got a block sitting on the back of a flatbed truck. The truck is pulling away from a traffic light after the light turns green. So as the truck travels in this direction, the block is going to try to stay at rest. So in order for the block to move, friction has to pull it forward. Think about if there was no friction. This would go right off the back of the truck. Not because it went backwards, but because the truck pulled forward, and objects at rest want to stay at rest. Okay, so friction pulled it forward. Okay, here we have a truck that's moving down the driveway at a steady speed. So we don't need friction. because objects that are in motion will want to stay in motion. We don't need a force to keep them moving. Here we have a truck going to the left again, but this time it's slowing down. And I hope you realize if it's slowing down, this box is going to try to continue to go forward at a constant speed. So in order for that thing not to crash into the truck when the truck stops, friction has to stop it. So again, without friction, this thing would have kept moving to the left. So friction must have been pulling it in this direction. Here we got a truck that's backing up. And in order for the box to follow the truck, friction is going to have to pull it in that direction. The box would want to stay at rest. So in order for it to move to the right, as you saw, friction would have had to pull it to the right. So I know we covered a lot of ground today. I'm not going to ask you to do anything other than take the notes and think about them. A couple days from now, I'm going to give you a little Google form to make sure you remember all of these key ideas. All right, so that's it for today.